Module 4, we have rational functions and equations. Rational functions and equations. Let me get this down there. Oh my goodness, I messed something up and now I can't undo it. Move. Okay, there we go. Functions and equations. Okay, dig this about it. There we go. That'll work. I guess, okay, so we left off, module 3 was talking about polynomials. And we had talked about with polynomials, we took functions that seem to be getting more complicated with x to the 0, x to the 1, x to the 2, x to the 3, x to the 4, 5, 6, as far x as you want to go. Having these powers of x in our functions made things more complicated and they made more wiggles along the way. X to the 5 being 5 pieces, it would be like up, down, up, down, up. And of course, we've made mention that x to the 0 is the same as a constant function, which just has no x's in it. It would be something like f of x equals like 3 or something where there's no x's at all. So we say, well, that's like doing x to the 0 because there's no x's, And of course, well, whatever, that's a good enough explanation of that. And so rational functions, the reason these come next is because they are an extension of exactly that idea, expanding that same idea even further, saying, well, what if you didn't stop at complicating your functions in powers of x by going 3, 4, 5, 6, 7, and then that's as far as, go as far as you want to go with those. That's all polynomials. Well, if we keep going, if we're like x to the 4, x to the 3, x to the 2, x to the 1, and the simplest function so far is x to the 0, I guess the only place you could go from there would be, well, at least the next logical place to go would be, well, is there an x to the -1? Is there an x to the -2, x to the -3, Could I keep going in that way? Is that, is there a way to make sense of that, And so, if so, what does that mean, Oh, sorry, my function, or sorry, my phone making noises. There we go. So here's what I'm thinking. Okay, notice with me. Well, okay, so spoiler, of course, these guys are where rational functions come in. And that's why this is studied right after module 3 with the polynomial functions, because it's really just expanding the idea or extending the idea of polynomial functions into negative powers of x. And so let's talk about what that looks like, though. So suppose for a second you had x to the 3. We know what that all looks like. It's x times x times x is x to the 3rd. But then if I started saying take x to the 3rd and I start dividing out some of the x's, if I divided out an x, then it's like, well, I'm timesing a bunch of x's and then I divide one out. Well, then I have x to the 2 left over, which is this guy, of course, And if I divide out even more, then I have x to the 1 left over, which is, x to the 1. And then I notice, though, at some point, here's our first weird situation, is if I divide by just as many x's as I times by in the first place, or if I had x to the 3 on top, divide by x to the 3, all the x's cancel out, and I got x to the nothing, And you could tell by just looking at them that there's no more x's left. So that would be believable to call it x to the 0 because there's no x's left over. They all canceled out. At the same time, and you could do that by algorithm too. You could be like x to the and then 3 minus 3 and minus it, and 3 minus 3 is 0, and that still works. One thing that's interesting about that, just as a side note, is that you'll notice that x to the 0 does not equal 0. You'd figure x to the 0, like what else could it possibly equal? But it typically, unless there's a number with it, it equals 1, because at the same time as you could say, well, there's no x's, somebody asks you how many x's are left in this expression. And you'd have to tell them, well, they all canceled out, there's no x's left. So you could say, well, this is x to the 0, and that would be true. But if somebody said, well, what does this equal? Well, what I see is a bunch of some number dividing by itself. And you would then, and we know what that always means is like if I had some number like say 5 dividing by itself, 5 goes into 5 not 0 times. 5 goes into 5 one time. So when we have a power of 0, it doesn't equal 0, it equals 1 for that reason, because it's something dividing into itself. Sort of a now bridging further into this new world of like, how do we interpret negative powers of x? Well, I guess if we did something like this, say we had something like, well, x to the 2 in the first place over x to the 3, if I have more x's on the bottom than I do on the top, what would that look like? How do I interpret that? If we handle this by algorithm like we did before, where we're just like, well, I'll just minus the exponents because that seems to be working. 3 minus 3 made 0 and stuff, and you could do it with other ones. We could handle that here, and it first off indicates to us an idea that we might be going into the negatives here, because look at this, we're like, well, 2 take away 3. If I take powers of x, 2 take away 3, well, that is -1. X to the 2 minus 3 is x to the -1. So whatever -1 power means, it seems to indicate that it's something involving with, well, there's more x's on the bottom than on the top. And if I simplify this down, then we'll start to see even more perspective on it. So 2 minus 3 is the same thing as -1. Maybe I won't need to write that again. I'll just arrow it up there and say, well, this seems to be what that is. But if we look at that by, not worrying about our algorithms for canceling things and all this stuff, but we just kind of look at it naturally and let things cancel, we get to make another conclusion where we see, well, x over x cancels, x goes into itself once, whatever. And then we're left with nothing on the top except maybe a number 1, but then on the bottom, there's still an x there. And so what we see is, well, there's only one of them on the bottom. So I guess you could call that x to the 1, but it's on the bottom being divided now. And so if I look at it from this way, we make this conclusion where it's like an x to the 1 on the bottom. But if I look at it in the old fashioned, like minus the powers way, it means that it's x to the -1. So it seems to suggest to us that x to the -1 power, well, now we have a way of thinking of that. Like, what does that even mean? Well, it seems to mean, what it means is that we are dividing by x once. And so just as in the same way as powers of x's and powers of numbers, they normally represent, well, how many of these do I have and how many are timesing, If I have x to the 3, it has a meaning to us. It means that I have 3 of them, and what they're doing is timesing, Well, now we have this idea of saying, well, if I have a negative power, like x to the -1, x to the -2, x to the -3, it seems to still suggest, oh, I have 3 of them, I have 2 of them. It's how many I have of them, sure. But what they're doing is the opposite of what they were before. Just in the same way as negatives are the opposite of positives. Now we have that negative exponents, they don't necessarily mean that there's a negative number involved in anything. What they mean is they are doing the opposite of what exponents normally do. They represent something opposite of what's normally going on with exponents, rather. And so if I have x to the 3, that stands for 3 x's, they're all timesing. Well, if I have x to the -3, if I have x to the -3, I guess what that represents is 3 x's on the bottom all being divided, and you could still put times's between them or something, but the idea is that we're emphasizing that they are all being divided. Or you could maybe, it'd be better to rather say it's like 1 over x to the 3 is the way we say it. This is us saying, well, it's still 3 x's, but they're being divided now. Instead of being timesed, it is the opposite of timesing that's going on. It's dividing. And so that's what a negative power means. And that's what rational functions are talking about. They're an expansion of our polynomial world in that we're moving into negative powers of x. But what does that mean? It means that we're just putting x's on the bottom of functions now. We are dividing by x's and not just timesing them anymore. And so when you see fractions, you might see fractions that have x's on the bottom now. And so that's introduction to, what rational functions are. And then big idea about what we'll be looking for is, here's some things that show up here. Say I took a function, a rational function. Well, we'll start with a simple one. What if I gave you 1 over x minus 2 or something like that? A new property that we're seeing in rational functions is that they behave a little bit more peculiarly, or they just, they have funnier behaviors than polynomial functions did. Notice in particular, this particular one, if I have, say I'm plugging in numbers into an input-output table, x, y, in, out, like we do, and I'm shooting numbers in there and I'm plugging in 1 and a billion and whatever else you want to do. Something funny we notice is that there's a problem when I'm plugging in the number 2. Problem. There's a problem with that. Not that it's obvious that it's a problem. Some of you guys might notice that it's a problem, but what becomes a problem about it is that if I plug in a 2 there, that's 2 minus 2 on the bottom. That is a 0 on the bottom. And a 0 on the bottom of a fraction is bad news. This makes this 1 over 0. That's bad for us. Because 2 minus 2 is 0 on the bottom. So 1 over 0. That's bad for us because it's hard for us to know how to interpret that. Because, well, I mean, this could be maybe a sidebar, but we could talk about why that's bad, just because it's relevant to our experience through over the whole module here. If I just tried to divide 1 divided by 0, that's us saying 0 goes into 1 how many times? And any number of ways of thinking about this, it still lands us on, I don't know how to answer that. Because, 0 goes into 1 how many times is us in one way saying, well, 0 times what number, 0 times what could I put for an answer up here? 0 times something equals 1. And 0 times nothing equals 1. 0 times 0 doesn't equal 1. 0 times 1 doesn't equal 1. So I can't say it's 1. I can't say it's 0. That would be our best guess. But 0 times 0 is not 1, and 0 times a million is not 1. It's not going to work. And so that's what we notice about these is when I'm dividing by 0, not only can I not figure out a number that would times by 0 to get me a 1, but it doesn't matter what number I put here. I'm not even getting any closer because 0 times, even if I did put like say a billion or something up here, I'm not actually getting any closer because a billion times 0 is still not any bigger than just 0. It's not even approaching 1 at that point. So this is problematic for us. So then we're like, okay, well, how does that affect what goes on in the function inputs and outputs? Obviously, there's some bad something that happens there. And so that's where we need to start looking. So if I'm thinking inputs and outputs, the X values are our inputs, right? So we're like X value, that's sideways numbers. So 1, 2. X values are sideways numbers. So there's positive 2 for X. And I'm going to just put kind of a dotted line here that indicates that something weird happens right there. If I plug in a 0 for X, that's whatever. If I plug in a 1 for X, that's whatever. If I plug in a 2 for X, all of a sudden something is bad right there. And so what we'll notice over time, and we don't, this is big picture stuff, so we don't have to get into it, but feel free if you ever want to go on the side and plug in like a 1, a 0 and a 1, and then start going like, well, what about 1.9? And what about 1.99 and 1.999? And see what goes on when you get close to that, plugging in that 2. And that'll start to indicate some behaviors for this. What we tend to see with these situations, guys, well, actually what we always see in these situations is a weird infinity behavior. And so you can feel free and plug that in and try it out or whatever. But since we don't want to get into nuts and bolts here, I guess what's going on with something like this is you see that everything's going normal, everything's fine. And then all of a sudden, let's make that look a little bit better. All of a sudden the output skyrockets up or sometimes down. Anything it can do to avoid hitting that line at X equals 2, because it knows, it's not like it knows, but because when we approach that line, it suddenly is like something has to happen. We have to avoid that too, because it's such bad news, and okay, it's not like the function is trying to avoid the line, but what it seems to be is that suddenly you see this behavior jumping up or sometimes down straight up to infinity. You can think positive infinity is like the top of the universe. If you're playing Pac-Man or something like that, and then actually if you're playing Pac-Man, you'll notice if you ever go to the top of the screen normally you have to go left and right in Pac-Man, but say you were in Asteroids or some game like Pac-Man like that, and you go to the top of the screen. What you might remember is that if you go to the top of the screen and pop out from the top of the universe, then you come back at the bottom of the universe, and that's what we see with these functions a lot of the time is sometimes they don't come back down from the top, sometimes they do. But other times, like in this function, I believe what goes on is that as you approach the 2, like you go up to infinity and then somehow you break through that wall without touching it, without ever touching the 2, you hit, you go up to the end of the universe and show up on the other side of it, on the bottom of the universe, and then come back down. And that's what's weird here. And so that becomes a topic of interest because but it just folded around the edge of the universe, however you want to look at that. But it definitely is a new behavior here because of some unattainable output around the number 2 input. So watch out for that. We call this vertical line, it's called a vertical asymptote. You'll be dealing with some of those. And then, okay, other functions, things that come up. We still in this, there we go. We still in this module are looking at x-intercepts and y-intercepts. That won't go away. But suppose, well here, let's, okay, just big picture stuff here. Suppose if we had a function that was like our last one, maybe we have x minus 2 on the top this time, and then x plus 5 along with it, but then it wouldn't be a rational function if we didn't have stuff on the bottom. So what if we have x plus 3 and x plus 5 going on? Some things that are involved in that is you'll notice for one, well, if I plug in a -3 here, -3 plus 3 is bad news just the same, you know? So that would indicate that we'd have a 0 on the bottom. If I plug in into our function some things that are worth noting, x, y, in, out. We're noticing if I plug in a -3, that's bad. Also, if I plug in -5, that's bad news, you know. But you'll notice they're different situations because -3 plus 3 makes a 0 on the bottom. And I suggest to you that'll be kind of like what we were just dealing with. You know, we don't necessarily need to redraw that. It'll be, or here I go redrawing it, but we don't need to spend much time analyzing that. Here's -3 on the x line. And probably there's some kind of a weird infinity behavior on that, you know. I don't know exact picture, but say it went up or down forever. And then it would either come back down from the top of the universe or start back up again from the bottom of the universe, something like that. But then notice that if I plug in -5, -5 also puts a 0 on the bottom. But it's weird because it zeroes out the top at the same time, you know, because they both have an x plus 5. And that's a different situation you'll run into. Because and what's interesting about it is that you notice outside of plugging in a -5, where something weird happens, it's kind of like no matter what else you plug in, you could basically just cancel these factors out because it's one thing over itself. So they're always just cancel out. Outside of this funny idea about getting a 0 on the bottom, where we'd have to kind of figure that out, it looks like you could plug in a 4 if you wanted to, or a 10, or what does it really matter? 4 plus 5, that's 9. That's 9. 9s cancel out. Well, so does 5 plus 5 cancel out. 10s cancel out. You know, it doesn't really matter what you plug in. They'll just cancel out as though they weren't there in the first place. And it would be really just like this function of x minus 2 over x plus 3, except at the point x equals -5. 1, 2, 3, 4, 5. 1, 2, 3. Yeah, 4, 5. That was -3. So then here's -5. Something weird happens here with our function also. So what is that, you know? And I'll give you a chance to investigate that, except let me hear about basic idea. What goes on with that? Let's see if I can, yeah, there we go. Is that instead of seeing things go out to infinity, what's funny about it is that since the function is behaving as though these aren't even here, it's kind of like nothing impressive is going on in any way until you put in that -5, because -5 plus 5 is weird, but nothing else seems to affect anything at all, as though they were canceling out. So what happens is we have just a hole in the graph where there suddenly is a dot that's missing. And then it goes on with the rest of its life and it becomes an issue somewhere else at the -3. And it's weird. We call this a removable discontinuity, or else say just a hole in the graph. And so those show up here as well in module 4. We have infinite discontinuities. We call these vertical asymptotes, the lines that cannot be hit. We have these removable discontinuities, or what they call them a hole in the graph. That's weird, you know. And we also still have x-intercepts and y-intercepts, because you'll notice at places that you will still at times be crossing over, say, an x-axis, or crossing over a y-axis as I've drawn here, or whatever. So those are to be handled, and you can actually pick those out from the equations pretty quick once you get to know them. Those are all the new dynamics here. One other thing is what we noticed about polynomials is they wiggle around for a while, and once they're done wiggling, once they have 1, 2, 3, 4, 5, 6, 7, say this would be an x to the 7 polynomial maybe. Well, then it just goes skyrocketing up forever. Or it might, hey, you know what I meant to do. Or it might just tank downstairs forever after that, you know. But either way, Either way, something goes on forever with it just saying, I'm done wiggling. There's no more wiggling to do. And I'm just going to be keeping on going either up or downhill forever. Well, that happens with some of these as well. But what you'll also notice with rational functions is sometimes instead of them skyrocketing up forever or tanking downstairs forever, what they'll do is they'll start to taper off forever and they just kind of flatten out forever. And that actually gives us what we call a horizontal asymptote. Watch your, keep your eye out for that term as well. We call it a horizontal asymptote. It has to do with the long run behavior or the end behavior of the function saying, well, if I plugged in 1,000,000 or something like that, what would this end up looking like? And so it depends on some things involved in the function we don't have to get into right now. But we'll be watching out for that because sometimes these rational functions do that as well. So these are all the new properties that we're running into when we put x's on the bottom of equations, as we run into all kinds of new weird things in the world here of functions. Is we have walls that we cannot penetrate at these vertical asymptotes, shooting out to infinity, coming back up from negative infinity. We have holes in the graph that suddenly are just missing. And now we also have this behavior where we don't have to skyrocket out or taper down or or tank downward forever, but we might just end up flattening out forever, where your function just ends up being almost a straight line for the rest of its life, flattening out. Okay. Only other thing, that's most of the big picture stuff. Only other thing is, do watch out. We have equations to solve in here. And so some equations to solve, well, here, if we had, say we had a dynamic of something like this, equations that have x's on the bottom of them. So we had something like this. We have 5 over x plus 3 and 3 over x equals 7. I don't know. Yeah, 7, we'll say, over x and x plus 3. You'll see equations like this that have x's all over the bottom, and sometimes they'll have x's on the top as well. It's whatever. And then we'll have techniques about them. We don't have to get into techniques about how to solve them. Just watch out for this. Sometimes you get x equals whatever. And new dynamic involved in this is, remember, if I say I got x equals 12 as an answer, that'd be fine. It's probably not that, but because I didn't bother to solve this one. But say that would be fine, But if I got x equals -3 for an answer, there's a possibility you might get an answer like this. That is not fine. That is bad as well, because we have this new property that we've been trying to avoid, where it's like, well, or that includes situations that we try to avoid, where we might be able to have an answer that we could plug in that would be very bad news. Because if I plug in -3 plus 3 as an input here into this equation now, well, -3 plus 3 is a 0 on the bottom. And that means we would get this, we call it undefined. It's not an answer, really. It's nothing that could actually work for us because it's not a number that we understand how to, it's not really a number as we define it. And so we don't know how to deal with it. And so if you ever get a problem in which the answer is something that would make this undefined, it puts us in a funny situation, because that means the only number that x could be, according to your algebra solving, is also one of the only numbers in the universe that it absolutely cannot be. And so sometimes you'll end up with no solution at all. Or maybe you had 2 solutions. Say you came up with both these solutions and one of them is bad. Whoops, wrong one. And one of them is bad and you get to only keep one of them. Sometimes there's no solution at all that works. These are things to watch out for. Anyway, that's all I wanted to mention about this. That's big picture stuff. A lot of asymptotes and weird things when you get x's on the bottom being divided here. We call them negative powers of x.